Hey everyone, so in my last video I did a simple linear algebra problem where we used matrices to solve systems of equations in a 2x2 matrix. What if you wanted to solve a more complicated system? Let's say we have 3 equations and 3 unknowns. You'd follow the same procedure of using the calculator and you'd be able to solve the system really quickly rather than using a whole bunch of substitution and going back and forth. But what if you had to have no choice but to solve it by hand? I'll show you the procedure that you need to go through. So as usual, we say that AX equals B. And let's say that A equals a 3x3 matrix, and we use the matrix notation I was showing earlier. Where, the first one would be the row, and the second index would be the column. And then let's say that variables we want to solve are x1, x2, x3. It could be anything. A lot of the times you might be dealing with 3D systems that might be x, y, and z. It doesn't matter what we call them, as long as we can solve it in the end. And these equations might have some extra numbers sticking out that aren't multiplied by the variable, and these go on this side. So let's say we want to find determinant of A. You actually have to, for a 3x3 system, you have to use what you call a cofactor matrix. So it's always going to be this. And I won't prove it in this video. And what you do is, you kind of have to make minor matrices. You partition this 3x3 matrix into little 2x2 matrices. Going index-wise through it, you have to either complete a row or a column. Like, I'll show you, and you'll see it within a second. We start off with A11, and we have to multiply by the minor of the matrix. So what you do is, and I use this trick a lot, and I show it to many students, is when we're doing it for this cell, kind of put your hands over that column it's on, and put your hand over that row it's on, and this will be the accompanying matrix that you need to find the determinant for, and you multiply it inside of this. So let's undo that. And it'll end up being A22, A33 minus A23, A32. And we do it for the rest of them. So let's say we want to use these along the row. You can pick anything. You don't have to go along this row. You could pick any row to go across, as long as you use this cofactor matrix. So the thing is, since we're using this cell first, it's multiplied by +1. If we use this one next, we have to do it by negative, and it'll be the same procedure. You put your hand over this one, and you find the determinant of what's left. And by doing this, you can solve bigger and bigger matrices by just splitting them up into smaller problems. And then the last one would be A32 minus A22, A31. And that'll be your determinant. Simple. So this is a very generic form. Maybe you'd like to see an example instead. So let's say A equals this. And you can use, and as I said before, you can use any row or column to go across, as long as you use this little cofactor matrix. So to make life easier for yourself, if you see zeros, use that row or column. It'll make your life a lot easier. You'll have to do a lot less arithmetic, and you'll have a much lower chance of making any mistake. So what'll this be? It'll just be this. Minus 6, 8. And then it'll be... I'm not even going to bother doing the inside, because it'll be multiplied by 0 each time, and 0 multiplied by anything inside will just be 0. And this will end up being -6. That's good. What if your life was a bit more tricky though, and you didn't have that? Let's do another example quickly. Let's say there's no solution to it, and you just have to brute force your way through it. That's fine. You just use the formula again and just go across anything. Whatever you believe would be the simplest computation. If you don't see zeros, maybe ones would be slightly easier to deal with instead. And you know, we're just going across this row right now, but remember, you can also go across any of them. Just remember that cofactor matrix so you don't mix up the positives and negatives. If you mix up a positive or a negative, you'll get a completely different determinant from the answer, so watch out. And then we'll simplify it. It's 2. Okay. Yeah, 3x3 matrix doesn't take too much work, and you can check because sometimes you're given equations, but sometimes you have to make equations yourself by doing balances on systems or bodies of objects. So you can see if your set of equations makes sense so far, because if it's 0, you can't really solve the system of equations, and that might be indicative of some kind of problem. But if it's non-zero, you know, you can, that's a good check. It's a good sign that, you know, you can proceed. Later on, there's a lot of different operations we can do to see how easily you can solve a matrix, whether or not it's what you call ill-conditioned. But for now, this is enough. There's also something else I'd like to cover. Sometimes you might mix up signs and stuff. If you don't like this method, there's actually another way to do it. So there's one equation you can use, and it's just called the method of Sarrus. And I'm going to change the notation a little bit because now it's easier to understand with A, B's, and C's. Let's say we have this kind of matrix, and you want to find the determinant. What you do is kind of draw a little imaginary matrix underneath it, and you kind of circle the diagonals. And the formula is just this, and you don't have to memorize it. This is like a graphical way of doing it in case you panic and forget on the exam. The determinant will just be A, E, I, and you can prove it as well. It's just the same thing we've always been doing. So those are the first 3, but then for the last 3, you go in the opposite direction. And it gets messy, but you'll have to do it for yourself on paper. That'll be GEC minus AHF minus, DBI. So last 3 are minus, and the first 3 are positive. And yeah, you can get the matrix just doing all of that as well. Not matrix, sorry, you can get a determinant by just doing these simple operations. So watch out for that. So sometimes you might even get asked on an exam to solve the determinant of a 4x4 matrix, or maybe a 5x5 matrix. What you have to do is you just have to take advantage of the zeros. I know once on my final exam in linear algebra, I got asked, there was a nasty 5x5 matrix, and what you'd have to do is, if you just looked carefully, you'd see that one of the columns in particular had a lot of zeros in it, and then you could just turn it into a 4x4 matrix, and then you turn it into a 3x3, and you just keep doing that until you make the problem easier for yourself to a point where you can just solve it yourself, you know? Just always be careful of arithmetic mistakes. For this level, it's really easy to just mix up a sign, and what will happen is you might end up getting a false determinant that you think is 0, but it's not really 0, and it turns out maybe you could have solved the problem in the first place, but now you made a mistake and you found out you can't, you know? So always double check this. You know, there's actually lots of programs available. You might even be able to use like Wolfram Alpha or different kinds of programs to double check this. For myself, I use MATLAB. It's very useful. If you found the content in this video very helpful, please give it a thumbs up and subscribe to my channel so you can be the first one to receive updates on videos coming out like this. Thanks.